Watch a modern automated assembly line, and you will see heavy steel arms moving with incredible speed, stopping within a fraction of a millimeter. It looks effortless. But underneath that movement is a complex translation problem. How do you take an abstract, weightless line of digital code and use it to control heavy physical mass? The answer is mechatronics. It is the deliberate physical intersection where mechanical engineering, microelectronics, and software control converge. Because no matter how sophisticated a computer's software might be, a machine's ultimate utility is strictly limited by its ability to reliably manipulate the physical world. The simplest way to attempt this manipulation is through an open loop or feed-forward system. A controller blindly issues a command to a motor, telling it to take exactly 100 steps, for example, and assumes the motor did the job. The physical world rarely behaves exactly as commanded. Moving mass requires actual force. Friction, unexpected resistance, or a slightly heavier payload will immediately disrupt that intended movement. When a motor tries to force that movement without checking its progress, it experiences rapid, unmonitored changes in acceleration. In physics, the derivative of acceleration is called jerk. This causes damaging vibrations and severe mechanical stress over time. If a robotic arm carrying a heavy payload suddenly hits a jammed gear in an open-loop system, it won't stop. It will keep forcing the movement, causing the machine to wildly overshoot its target, smash into its surroundings, or literally tear itself apart. To achieve true physical precision without destroying themselves, machines cannot rely on blind instructions. They need a way to actively perceive their own physical state. To solve this blindness, mechanical engineers rely on a specific hardware layout called the Input Process Output, or IPO, architecture. It relies on three distinct components: sensors that gather data from the physical environment as inputs, a microcontroller or central processor that acts as the brain, and physical actuators, like motors, that serve as the output muscle. By attaching a sensor, like this position transducer, directly to the moving mechanism, the machine gains the ability to monitor exactly where its physical parts are at any given microsecond. This creates a closed-loop control system. The machine constantly measures its actual physical output and feeds that exact data straight back to the brain to inform the very next command. Inside that processor, a mathematical algorithm called a PID controller takes over. It constantly subtracts the physical feedback from the original command to calculate the exact degree of error. This chart shows how the system tries to correct that error over time. First, the proportional element acts as the raw drive. It pushes the motor toward the goal with a force proportional to how far away it is. In most systems, this raw drive usually causes the machine to overshoot the target. To fix that, the integral element steps in. It continuously adds up past errors to ensure the machine doesn't get stuck just short of the target due to real-world friction. But this can cause the physical motor to oscillate or ring as it bounces around the target line. Finally, the derivative element analyzes the rate of change to predict future error. It effectively applies the brakes as the physical target approaches. This smooths out the movement entirely, allowing the motor to settle perfectly onto its target. This high-speed mathematical balancing act outputs a single, flawlessly modulated pulse to the motor. It takes the messy, unpredictable physics of the real world and forces them into an act of perfect precision. This multi-layered calculation is happening thousands of times every second inside almost every modern automated device on Earth. You will find this logic governing accessible microprojects running on compact microcontrollers like this Arduino for student robotics or wearable tech. Scale up to the macro-industrial level, and that exact same mathematical logic drives massive, ruggedized, programmable logic controllers running entire factory automation lines. Whether the system is a 5-volt hobby kit or an automotive assembly robot, the core logic governing its physical movement remains identical. Traditional machines operate by exerting brute force. Modern mechatronic systems engage in a constant, high-speed conversation with their physical environment, applying exactly the right pressure to hold an object without breaking it. Modern automation functions through this perfect physical integration, where the digital mind and the mechanical body operate as a single, responsive unit. Technological progress moves forward when systems learn to continuously listen, correct, and adapt to the world they are designed to change.